Thank you so much. It surprised me how happy I became when I became a professor. So it made me so happy. I was jumping. I didn't expect it. Maybe, professors are this group of people who are very, very, serious and wise, and I like to make jokes all the time. So, so it did thrill me, and it gave me huge pleasure. But I would be naive to say that that's something I did by myself. There's a huge group of people behind me that made that a reality. First of all, my family, who supported me throughout these years to do my research, to realize my dreams. My colleagues at the university here in Leeds, which are spectacular. They inspired me. They collaborated with me. We wrote amazing papers. We discussed amazing physics. We wrote grants. We did. So for that, I thank them very, very much. I thank the support staff also of the university, of the school, that helped us at any stage we need something. And also thank the undergrad students that they have the enthusiasm, they ask questions, they want to understand better physics, and they fuse that enthusiasm to me as well. And hopefully I'll pass some of these messages on today. And also the students, they become PhD students at the school. They work with me, we write papers together, we discuss physics, and this is really, really one of the things that make me happy, and also one of the things that made me be here where I stand in front of you. So thank you for that. And of course, thanks to Marcin. I love a good mystery, okay? I read mystery books all the time. I can't think I could read any other book. I watch mystery movies, series. I want to find who done it, okay? That's what inspires me. That's really, I just do it all the time. And one of the beautiful things of physics is that there are many mysteries for you to go and solve and answer. Actually, is the next level of trying to solve a mystery is actually identifying the mystery yourself. So nature is huge, and you can accept it as it is, or you can start asking questions and create your own problem and then attack it to solve it. And this is truly wonder, truly beautiful. Today, I'll try to present you something usual in the physics world. I'll try to talk about quantum mechanics and what it is and what we can do with it and what are the big questions, open questions about it. And I'll start from, let's build it. What is knowledge? Well, we build knowledge from our experience. If we have a stone and we throw it up, then we know the stone will come back down, and that's certain. There's nothing disturbing it, it will come back down. If there is a wall in between, then the stone will come out, will bounce off and come down. And we can make a rule, a law about it, and accept it, and we're certain about it. But we don't have much experience about quantum effects, about little particles, about atoms, electrons, photons. We don't see them every day. They behave differently. They behave according to quantum mechanics. And they have a new set of rules that they satisfy. But how are we going to understand them? And this set of rules, they border to science fiction. They're very crazy. At the same time, they influence our everyday life. So let's put down some basic principles about quantum mechanics. What is it? Well, one of the principles is that objects behave both as particles and as waves. So that's a fundamental principle. This is a particle. This is something that is localized in space, and you can pinpoint it there. And that's a wave. A wave extends in space, and oscillates, and interferes. Now, what quantum mechanics says is that a particle, an object, is both a particle and a wave. But let's see what that means. It means that the wave is there, and it tells us something about the particle. It tells us when you have a maximum, you'll find the particle there. And there is probability to find it on this maximum, and there's some other probability to find on that maximum. So it's not certain where you will find it, okay? And this is the first weird thing. That's the first thing that makes quantum mechanics really behave strangely, because it could be here or jump there. And you're not quite sure until you make a measurement. And now, this wave behavior of particles just is everywhere. The whole universe is full of waves. And these waves can interfere. They can constructively interfere and create maxima, or destructively and create zeros. And this is fine, but if you think that there is a particle behind there, and this destructive interference makes it disappear, it starts making it a bit strange. You realize how strange that is. So quantum mechanics can explain many effects in physics, from electrons, photons, quantum optics, very, very successfully. But it contradicts our everyday experience. And the question is, do we just accept it? Do we accept what it is? Or do we question it? Do we try to explain it? There are strange things in quantum mechanics. Let me point out some very, very weird things. There is action from a distance. Okay? You can do something here and influence something down there. But not, that reminds you a bit of telepathy? Not really, okay? It's excluded, okay? So no one should take money out of you by using quantum mechanics for telepathy. It can actually allow particles to go through walls. It's something that defies our experience. So if I was demonstrating this experiment, this phenomenon in front of you, you know, like a magician, you would think, oh, there is a trick. You know, you say, okay, I know. If a magician pulls a bunny out of a hat, you're sure there is a fake bottom on the hat, and there was hiding there. Or if he disappears a coin from his hands, you know this very big sleeves and it's hiding in there. There's some logic on what is going on, and you probably naturally want to find out what happened. But in quantum mechanics, there are no double bottoms on the hats. There are no thick sleeves. Just weirdness just happens, just like that. And the question is, do we accept it? Do we just take these rules and say, okay, that's how it works. Let's move on and use them? But before doing that, let me first tell you what is at stake. Why is that question important? Why quantum mechanics is important? Well, it's very important because it influences our everyday life, not as scientists, but as people. First of all, it explains how chemistry works. If you solve the atom, the quantum mechanical equations for an atom, then you get the behavior of the outer shell, of the electron in the outer shell, and then it tells you how two atoms can actually interact or combine together to create a molecule, and that comes from the quantum mechanical solutions, and how molecules can combine together to create materials. It also tells us if a material is conducting or insulator. If you put a battery, 2 electrons from a battery on a material, will you see a current or not? That's, again, quantum mechanics. How? Well, quantum mechanics has describes a material in this way. It has these states, let's say, or these possible positions electrons could be, and some other states of other possible positions electrons could be. Now, the electrons all like to gather in one position. And if the other state is far away, there is an energy gap, as we call it, between them, then electrons cannot jump from this state, the valence band, to this state, which is the conductance band. If they cannot jump, it means that if you put electrons, they will not move, okay? Now, this description is fully due to quantum mechanics. You have to solve a quantum equation to get it. If this gap is very small, as in this picture, then it's possible that an electron, depicted here with this little ball, can jump from one state to the other and start moving. And that's the case of semiconductors. And if these states, actually, this valence band and conductance band actually touch each other, then electrons can move back and forth freely, and that's the case of metals. So if you put electrodes, then the electron can jump in the conductance band and move around freely, happily around. And this is, again, by solving a quantum mechanical equation. Okay? So, of course, we will know if something is conducting or insulating just by doing the experiment. But why it is conducting, you need quantum mechanics. Diodes, like that, the light that they emit without much heat, again, quantum mechanical effects. The transistor, you need semiconductors. You need to know quantum mechanics to build one. Lasers that we use, all these lasers we see in the discos, this is all quantum mechanics, really, there. Medicine, you need to measure, you measure actually the spin of chemical substances when you make these measurements, and spin is a quantum mechanical property, purely, it doesn't exist classically. So in order to make all these kinds of advanced medicine and find cures and diagnose things, you need quantum mechanics. And there is no way we could have a computer on our desk or on our lap as we have it now without extensive knowledge of quantum mechanics. It depends on quantum mechanics. We need to understand it and use it. So it's so common, it's hard to imagine, to see where quantum mechanics comes in. So in order to expose a little bit my worries in quantum mechanics, I'll take an autobiographical view on the topic. I'll pick up points in my life that more piqued in my concerns on quantum mechanics, and I'll describe them to you, okay? And I promise I won't show you any baby pictures or anything. It will be all kosher. The first thing I faced with quantum mechanics, the first difficulty, was as an undergraduate student at the quantum mechanical lecture. But let me tell you first something. When I was undergrad, before I take the module of quantum mechanics, I was, if I liked the module, I would sit down, study it hard. Before the lecture started, and by the end, I will know everything there is to know about it. I'll read books or ask questions. My lecturers are really search about it, and I'll be confident. Won't do it on every module, the ones I really liked. So I will smash it, as we say it, right, the topic. So when I was going to get into quantum mechanics, I thought, I know there are problems there people didn't understand in quantum mechanics. I'll apply my same logic there. I'll smash quantum mechanics, all right? And then I was faced with the huge questions of quantum mechanics. And of course, quantum mechanics smashed me in a sense. The first kind of hit I got was with the uncertainty principle. It tells you that you cannot know the position of a particle and its velocity with infinite accuracy. You can't know them well simultaneously. Okay, and that's very strange. It puzzled me. Why can't you know both of them at the same time? So I tried to find some mechanical analogs that will justify that to me, exactly this behavior. And for example, if you have a particle that travels like this, then that's me. I'm not lying on the sofa. I'm actually doing an experiment. I want to measure this particle where it is. I'll throw some photons on it, okay, and then some light, and this light will bounce back and it comes to my eye, and then when I see that light coming back, I'll know the particle was right there. But by doing so, this kick the light gives to the particle will make the particle change its momentum. So while I've seen where it's positioned, its momentum has changed. So that tells you that, oh, you can know both of them. And I was very, very happy with this mechanical analog. Actually, it does exist in some quantum mechanical books even nowadays, but it's wrong. This is just a scattering process that you can look at it classically with your usual logic, or quantum mechanically. The whole thing could be a quantum mechanic, incorporated within quantum mechanics. That's just a scattering of light through particles. So it can't explain you anything about quantum mechanics. Quantum mechanics can explain it, if you like. So this is not the way to go. The uncertainty principle is fundamental. You can't understand it, even if you look deep in here. After my undergrad studies, I did a PhD in mathematical physics. I worked on elementary particles. I worked on string theory and membranes and so on. And I have to admit, during those studies, I didn't have to worry much about quantum mechanics. I just used it as it is. Okay? So I'll call it the dark ages of quantum mechanics for me. I take it as it is. And at some point, I got interested, by lack of necessity, I got interested on computers, especially on quantum computers. But let me give you a short overview of 2,000 years of computers. This is the first computer built that we know. This is the Antikythera mechanism. It was a guy from Rhodes made it, not me, 2,000 years ago. So this mechanism, you put the date, and he finds the positions of the 5 known planets at that time, and probably could tell you more things about astrological phenomena. It was a guy who actually studied the motion of the planets, so he put these things down, and then he constructed himself the device. Okay, so both he made the studies, and he constructed it. And we don't have any of this technology going to the society, because at that time, this device was used as a gift from one king to another king. Like a lava lamp you put on your desk, and it looks nice, and you can impress your visitors. Oh, how nice. That's what it was used. So it stayed within very confined boundaries. It didn't go, nobody had watches 2,000 years ago that should with this thing. Looking there. Then we have this, so this is an analog computer. This is a digital computer, one of the first digital computers, Robotron Z9001, yes. And then the object of my desires, the D-wave quantum computers, yes. So this is, people started now building quantum computers. You see, a couple of decades ago, some smart people said, okay, quantum mechanics behaves strange, has a strange logic. Let's use this logic and make programs, computer programs, based on this logic. And what they found is that you can solve extremely difficult problems by using quantum mechanical logic. So you can solve them very, very fast. You can factorize large numbers. You can break into bunks and encoding systems and so on, if you had a quantum computer. Okay. Now, this is a quantum computer that can run this software, but it's a very, very, very crude quantum computer. It can do very simple tasks, much simpler than our usual computers can do. But it does work with quantum mechanical principles. We just need to make it more and more sophisticated. The problem is that these are highly unstable. Quantum states get distracted easily. So the problem we face in order to make a large, stable quantum computer, how can we do it? How we can have quantum mechanics and stability together? Next, we move to 5-10 years back in my life. Of course, we're still there. I'm at the Dolomites, at the Hat, with a friend of mine, Paolo Maraner, and we're fairly senior scientists, and we thought, like, why don't we try to explain quantum mechanics with classical mechanics? Can we do it? One of these topics you shouldn't touch when you're young, okay? Can destroy your career. So we thought, like, okay, nobody is looking. Let's try to do it. So we tried to find classical analogs that reproduce quantum mechanics. And we successfully did it. I was really, really excited. He came with an amazing idea. And then you can describe local objects, like one particle or a spin, by a classical analog. So you can find a local description. And then I went to colleague scientists like David and told them about this, and he said, sure, people knew that since a long time. The hard thing is to find classical description of quantum states of two particles. And for that, John Bell devised a test that can distinguish between completely classical objects, any construction, even magicians, anything, the best magician on earth. Can they imitate quantum effects? The Bell test can tell you, no, that was classical, and quantum stuff can do something more, can do something different, and we can distinguish between the two. So what I would like to do, actually, in front of you, is perform this Bell test, the experiment that led to the distinctions between classical and quantum physics. For that, I will need the description of spin. You can think of them as being two tops. A top can rotate this way. So with my right hand, I will call this being a spin up. And this one rotating the opposite way, my thumb points down, I'll call that spin down. So I have possible states of particles. And I will use two particles now, a red and a blue, and the left and the right, and either the left will be up and the right will be down, or the left will be down and the right will be up. So either I have them like this or like that. So there is always one up, one down, okay? So I have either this configuration or this configuration. Now, the wave property of quantum mechanics actually allows you to create a state that is the sum of the two. I will have this state and this state simultaneously, in the same way as you could have a particle here and here, probabilistically, of course, or quantum mechanically. So I can create that state. Now, I'm going to employ Alice Cooper and Bob the Builder, okay, to help me with this experiment. With such a name, you couldn't expect a different look back in the 70s, yes. So Alice here and Bob here, they will take each one of them one particle from this state, okay, and they will keep it. They keep it here, okay. They are far away from each other. They're not influenced. Now, Alice will measure this particle, and Bob will measure this particle. We'll measure the spin. Does it point up or does it point down? And, for example, if Alice measures this points up, then Bob necessarily will measure something pointing down, okay? Because the initial state tells you, I'll always pair them opposite, either like this or like that. So this is the outcome. Now, what they can do, both Alice and Bob, they can measure actually in an angle. They can measure this spin in an angle, and necessarily then the spin will be projected in that direction of measurement. And again, if Alice measures the spin up in this direction, necessarily this will point down in that direction. They are always opposite. But if Alice measures in this direction and Bob measures in that direction, then the answers could be random. They could both measure up and up because they are not on the same basis, okay? So it's possible to have that. Now, what the Bell inequality tells you, what the Bell test tells you, is that let's repeat this experiment many times, and Alice measures randomly in this direction or that direction, and Bob measures randomly, independently from Alice, in this direction or that direction, and then we count the number, how many times we measure both spins being up, one spin up, one down, or down up, or down, down. We just count how many numbers it is, because the randomly choose a basis is possible to have all of those configurations together. When they both spin up, down, it means that they measure on different bases, on an angle. But if they measure on the same basis, they will get an answer only here. So if they're random, they get all these numbers. And what Bell did is he created a function. He added and multiplied these numbers. He created a function of these numbers. And when this function, he said, if the preparation is classical, somebody prepared it classically with classical logic, I'll always find a number which is less than 2. I'll add them and multiply them, and the number I get out is less than 2. If I have a quantum state, then this will become larger than 2. So we have a conclusive way how to determine if quantum mechanics does exist or if classical mechanics explains it. So we need to violate this inequality. And what I would like to do is actually perform this experiment right in front of your eyes, right here. Okay? For that, I will need 2 volunteers. Okay? A boy and a girl. So please do come. Raise your hand. Who would like to come? Who would like to come? Yes, please. Here. And a brave person. Yes, please do come here. Hi, your name is?
Lisa.
Lisa, please come here. And you, your name?
Mel.
Mel, good, excellent. Please stand here, right here. In order to comply with health and safety, could you please put these goggles? Is it all right? Yes. You can put them even above your glasses if you need to. And what I would like you to do is to press this button or that button, just like that, okay, randomly. And you do exactly the same on this side, okay? Now, the measurements that you perform, the outcomes, are collected on my laptop, okay? So, and then I'll collect them, and then we see what happens, if we can actually violate the Bell inequality. Now it starts at the value 0. It needs to become larger than 2. So we need to collect lots of data for that, okay? So, very important that you don't get influence from each other. You just press, I'll hold this black sheet between you. So please, let's start the experiment. Please do press. Wait, stop, let's see. 0.3. Fantastic. That's good.
Was I meant to press it a lot of times or once?
A lot of times, yes. You keep on pressing, yes? Yes. Don't let him do all the job. Yes? Pardon?
Do it with the same button.
Same or different, you do whatever you like. You do as you like. So let's try once more. Yes? Right, please stop. Let's see what happened. 1.527, not quite 2. Okay, you're doing a great job. We need to try a bit harder. Okay, let's try once more. Okay, please stop. 1.991. Oh, once more. Let's not take failure. Yes, let's see. 2.638. Well done. Congratulations. Thank you. Thank you. Thank you very, very much. So, you might see it. Thank you so much for your help. Thank you. That's great. Wow. We violate the Bell inequality. Now, what it says is that if these two persons, they were independently choosing a basis here, pressing the black or the red button, independent from each other, then this violation means we have quantum mechanics. So let's see, who of you believes that they were completely independent? They didn't influence each other. Who believes that they didn't communicate or send signals or their opinions were influenced by something? Okay, that's 60%, 70%. Who believes they were actually communicating? Nobody? Okay. Okay, one person, maybe I need, yes, thank you very much. So, indeed, if they were completely independent, the quantum mechanics exist, which is great news. But let me take a step back, okay? Each experimentalist needs to have what we call the free will. Let me turn off the experiment, otherwise I can't cycle back home. Each experimentalist is exercising a free will. It decides a left or a right by themselves, independently. Okay? But a free will is a concept that is not modeled in physics. I can't mathematically model it. Maybe it has to do with randomness. Okay? Maybe if it's random numbers, then randomly they choose something. That's probably what comes closest to a free will, to these people being independent. If they were random, they're independent. But then again, could it be possible? I mean, that they're independent? I mean, the universe satisfies some equation, being classical or quantum. There's an equation, there's some initial conditions, there's an evolution. Everything depends on this equation and on these initial conditions. So it's predetermined. There's some equation that actually determines how things are evolving. I mean, we solve these equations at school or at the university to predict how a particle, how a stone will fly, and we know it will fall there, right? There's such a master equation for the whole universe. So things are not independent, they're influencing each other. They're depending from some initial, let's say, Big Bang or something like that. So how can we claim these two people were independent? So do you think they're independent, really? So we take a vote. Do you really think these two people were independent? Who believes they were independent? A good healthy number, but less than before, okay? Less than before. So, indeed, such debates about the existence of quantum mechanics and this very specific point I just mentioned is something that people from Einstein to Gerhard Toft, who got the Nobel Prize recently, they still claim that there's something wrong, that we should think about it. I don't take the position that quantum mechanics doesn't exist. I take the position that we should be thinking about it, okay? And we shouldn't accept, and we should use our logic or our imagination to think about quantum mechanics. Planet in Greek is the word planetis, which means a wanderer, something that moves without a purpose, back and forth, and you don't know why and how. And if you take a picture of a planet, actually from Earth, it will appear it does these zigzag motions. I mean, we know the planets make elliptic motions, but the Earth also makes elliptic motions. But if you put the Earth in the middle, and you say it's static, then the planets will appear to be going back and forth as we saw in this picture. They will be appearing to be going back and forth. And in order to explain it, the ancient Greeks used the concepts of epicycles. This kind of shapes, you know them if you've played ever with this. Very, very nice. It's a bit frustrating to manage to make it all through the end, but if you're patient, you can make these shapes exactly, which is indeed how the planets appear to be moving in the sky. What it is, let's try to analyze a little bit this motion. Let's say the Earth is here, the planet is here, and it performs this motion here. Okay. Like that. And I can model it, I can describe it by using two variables, the distance of the planet to the Earth and the angle is traversing. The angle is spanning. And so what the ancient Greeks did is they said, okay, I can explain the motion of the planets. Actually, it's not something that moves on a circle with constant radius and constant velocity, but there are two radii and two velocities, okay? So I can break that motion down to this radius and that radius, R1 and R2, and each one is moving with a different velocity. This moves here with a certain velocity, and this one moves around this center with a different velocity, and if you combine the two things together, you get the motions we had before. Now, this motion. I'll play it again because it took me agonizing long time to make it work. Here you are. So this motion actually can be described by two different radius and two different velocities. So they said, oh, we can explain the motion of the planets. But the astrophysicist is skeptical. Indeed, that doesn't explain anything because any motion of any particle, of any object, you can explain it by breaking it down to more and more circles and more radius with different velocities. Any type of motion, you can find a series of R's and a series of V's that can explain it. It's what we call a Fourier transformation, actually, in physics or in mathematics. It's going from the variables, the original variables R and theta, that can describe everything, into a series of R and V's, different than the R and theta, R and V's, that can describe anything else. So it's a concept of Fourier transformation. The ancient Greeks failed to explain the motion of the planets. But as a byproduct, they discovered Fourier transformation, which is an amazing concept. I would say, I think, it's an amazing concept. You can think of a motion of a particle in terms of R and velocities. So you can think in terms of the angle theta or in terms of the velocities v as parameters. Now, what I would like to do is think of a more complex system. I have one planet and I have a second planet nearby. I have two planets, okay? And I have a little vector. It will be a huge vector, but I have a little vector in my picture that points from one planet to the other. And I'm asking the question, what will happen when the two planets move all around and they come back to the initial configuration? What happens to this vector? So as theta changes, as the initial parameter we had changes, what can happen to this vector is it could wiggle a little bit. It can go like this. Yeah? But it's possible now, if I look at the motion of this vector, if I look at it in terms of the velocities, the relative velocities of the two planets, then it's possible that this vector actually rotates around. You won't see it in real space. You have to move to this new space of velocities, of this decomposition of the epicycles. And it's possible that this vector that points from one planet to the other in velocity space, not in real space, in the velocity space actually has rotated around. And such rotations are very, very important objects in mathematics and in physics. First of all, they are very stable. If that vector rotates around here, you could change the shape, actually, of this span circle to anything else. And as long as it goes around this central point, you have achieved this new effect, in new physics, a new mathematical object. Such encirclings, we call them topological. So the configuration, when it goes, only wiggles a little bit, and the configuration that goes all around the origin, they differ topologically, okay? And we use topological effects extensively in our everyday life. For example, we have this cup, okay? And if I hold this cup in my hands, it's pretty stable, it's all right. But if I geometrically change a little bit the shape of my fingers, then this cup will fall down, okay? So it's not a very stable configuration. On the other hand, if I have this mug, with a handle, if I put my finger around the handle, then the cup will stay with me, even if I change geometrically the shape of my fingers a bit. As long as I keep linked to the cup will stay with me at all times. It won't fall down and break. Amazingly, somebody has discovered this cup. It has two handles. That's my favorite cup, actually, because whenever I take my cup of tea and I want to go back to my office, I always have the keys in the other pocket. So I have to burn myself, get the keys, change again. So one handle is not good enough. You need two. Also, it's very sociable. You can pass that cup to somebody else. They can get it without burning themselves. I'm sure you were in that awkward social situation. This cup is a must-have for any decent office. I'm not quite sure what that cup is meant to do. Just somebody playing around, I think. Yes. So now, exactly the same thing as the system of planets we saw earlier on. That's a classical actually stability, topological stability, classical characteristic, can happen on quantum properties of particles. For example, you can think an atom that has an electron. The electron can be a cloud, like a wave, if you like. And you can think that I have many atoms or many positions of an electron that can travel on this ring. So there's an electron that can travel on this ring. For instance, there's a metallic behavior, if you like. Now, this electron can have a spin as the vector that was connecting the two planets. And as the electron goes from one position to another and comes back, this spin can stay the same. But if you view it in terms of the velocities, this new space that we introduce with the epicycles, it's possible that this in space, it doesn't rotate, but it's possible that in the velocity space, this vector does rotate. The spin of your particle does rotate. And in that case, you have a topological behavior. You have a quantum mechanical property of your system that is stable. And this is very, very important. This characteristic actually was awarded, it was discovered by these three giants of science, and it was awarded the Nobel Prize in 2016 for the topological phases of matter, just by discovering this new space, this rotation, this topological behavior in the spin of the electrons. Why should we care? Well, we want to use that in order to do quantum computation. You see, in quantum computers, the problem we have is that they're unstable. But these topological properties of quantum states, these stable trajectories, we can use, they're very stable. You can change many things in your system, and again, you get the same properties, quantum properties you want. So the idea, something we've been working a lot in my group, is to, and there's a book, also related book if you want to look more into it, is to use topological properties of materials in order to build a quantum computer. And I will stop here and I'll take questions. Thank you very much for your attention.